The next topics for the chapter on reactions in aqueous solutions would be to discuss in much more detail, and this is going to take a little while, the way we write molecular ionic and net ionic equations for precipitation reactions. This involves the discussion of solubility rules to predict whether a precipitate will form from a combination of aqueous salt solutions. In order to describe this section, we need to come to terms with what does it mean when we say something is soluble. In most cases, we're describing water solutions. And when they're dissolved in water, the substance will separate into ions. And most of the time, the solution will still be clear. It might have color. And we will label it in a reaction equation as AQ. That means aqueous. And as represented in this diagram here, for a sodium chloride crystal, when sodium chloride crystal dissolves in water, the sodium ion is going to be totally surrounded on all sides by water when it dissolves, and the chloride ion is also going to be surrounded on all sides by water. Notice that the oxygen side of water is attracted to the sodium ion, and the hydrogen side of the chloride ion is attracted to the chloride ion. Because the hydrogen has a partial positive charge and the oxygen has a partial negative charge. Okay, so when you have something, you describe its solubility. This is a numerical value that tells you how much of a compound will dissolve in a given amount of solvent at a particular temperature. There is a table, and there are a variety of different ways these are represented, but this one's from the McMurray textbook that gives us some guidelines for when things are going to be soluble in water. Ionic compounds commonly have some solubility in water, but that's not a guaranteed thing because some compounds are routinely soluble and other things have exceptions. So we need to get familiar with these gradually. You will want to have a good comfort with these as you work on more problems. They will become more familiar to you. So on the left, we see the list of things that are soluble. There will be certain ions. And at the bottom, we see certain compounds that are insoluble. The top group is notable to say that a compound is going to be soluble if it contains one of those cations from group 1A. So lithium, sodium, potassium, rubidium, cesium. All of those are going to be soluble routinely. No exceptions. That's helpful. In addition to that, another cation, the ammonium ion, is always soluble. You don't have to look for exceptions for those. They will be readily soluble regardless of where you find them. The next group of compounds is anions. A compound is going to be soluble if it contains one of the following anions. The halides, as in halogens, of chloride, bromide, and iodide, except that they have some issues. When they're combined with silver, mercury, or lead ions, lead-2, mercury, that's the funny mercury one, don't panic, you won't run into it often, will precipitate with chloride, bromide, and iodide. The other ones that have no exceptions that we like, are easy to work with, are the nitrate, perchlorate, and acetate salts. They are like the ones at the top where they have no exceptions, so they're always soluble. We like the ones that are always soluble because they have the least to make them confusing. And I'm getting extra line here I didn't want, sorry. And then the bottom set here is the sulfate compounds. And the sulfate compounds are usually soluble, except they're not going to be soluble if you combine them with strontium, barium, mercury, or lead. And so we're going to notice that mercury and lead are a common exception. Whoops. And for these two things. Lest I fail to say so altogether, there is a list of compounds that are actually not soluble very often at all. And these are the ones at the bottom of the list. The carbonates, sulfides, phosphates, and hydroxides are typically insoluble unless you have them combined with the cations from the top half of the chart, which don't have exceptions. So if you put carbonate with group 1 cations or ammonium, right, not ever going to be a problem. They're not going to precipitate. Sulfides are generally not going to be soluble unless you put them with those always soluble things that's shown up at the top, or a couple of other choices. calcium, strontium, and barium happen to be soluble for those sulfides. So the exceptions are going to be soluble in this case. And then these exceptions are insoluble by comparison. And then the phosphates are typically not going to be soluble unless you put them with the always soluble choices up there from the top, or the hydroxides likewise, except they do have three others, and that's calcium, strontium, and barium. That's a parallel to the sulfides, isn't it? So the calcium, strontium, and barium are in common with that set at the top. So certain things with the sulfides. So there's certain things kind of should get your notice as possible things to watch out for being exceptions. Get a bit familiar with these with time. So when it comes to solubility rules, you can't win. You just have to learn them. You got to commit them to memory, and the more practice you get, the easier they will become. All right, so let's do some examples and see if we can figure out which kinds of things will form a precipitate. What we'd have to do is look at swapping the cation and anion pairs and predict what things will be possible and whether they are still soluble. Okay, so if you mix sodium chloride and potassium nitrate, swap the cations with their corresponding alternate anions. So you have sodium with nitrate, and you have potassium with chloride. And we have to decide if there's going to be a possible precipitate amongst these. And we have to go back to our solubility rules to think about those. And so when we think about these compounds, the ones that are always soluble, I'm going to mark them, and then we'll decide where they impact these. Always soluble are things like sodium and potassium in group 1. Oh, well then both of these things are going to be soluble no matter what you put with them. And other always soluble ions include nitrate. So both of those have a reason to not precipitate. All right, next set of choices here. We have ammonium bromide. So if you swap the cation and anion pair, we put ammonium now with sulfate. And that would be 2 ammonium with 1 sulfate. And I didn't leave a lot of room. And then calcium with bromide. And in this case, to balance the equation or the formula, you need 2 on bromide. So which things on here are always soluble? Oh, ammonium, that's one of them. And I'm going to find the rest of them down here. That'll give us a clue. And so the ammonium with sulfate, if ammonium is always soluble, this will be aqueous. I don't care what you put with it, it will be aqueous. Then calcium with bromide, and you have to remember the rules. Well, halogens are not going to be soluble only if it's with silver, mercury, and lead. So in this case, it's soluble. Next pair. Swap the cation and anion pairs. Cation, anion, cation, anion. Remember, that's a +2. So barium is now going to combine with, and I didn't write the charges up here, sorry. I'll put them back in. +1. -1. The barium now combines with hydroxide, so in order to make an even formula, there better be 2 of them. And we'll have to decide if it's soluble. And then the sodium will combine with chloride. Oh yeah, we've seen sodium chloride. Well, guess what? That one's aqueous. We already knew that. Sodium chloride, anything sodium is going to be soluble. But what about barium with hydroxide? Well, we have to remember our exceptions here because we're not really good at these yet, perhaps. So let's go flip back to the chart and double check. Note here the hydroxides. The hydroxides are going to be soluble if they're with calcium, strontium, or barium. That means they will be listed as aqueous. When they're insoluble, we list them as solid. All right. So in this example, we will put aqueous because barium is okay, it's soluble with hydroxide. All right, next example, silver nitrate with lithium perchlorate. Oh, there's another one in here. The perchlorates are also always soluble. And so when you combine these, you swap the cation anion pairs, and silver now is +1 with a -1 nitrate, lithium +1 perchlorate -1. So silver with perchlorate is 1 of each. And perchlorate is always soluble, so we don't have to guess. And then the other compound is lithium, and it's nitrate. Oh, I made a funny N. And nitrate and lithium are both always soluble, so there's nothing going to precipitate in that example. Last set. Look at the cation and anion pairs. Magnesium is +2, bromide is -1, aluminum is +3, chloride is -1, and now we're going to swap the pairs. So put magnesium with chloride, there better be 2 of them to get the charges right. These are not all balanced, by the way. I'm making the formulas right, but I haven't balanced the equations. We could, but I'm just focusing on the states of the products for the moment. And now we're going to combine aluminum with bromide, and it's going to look a lot like aluminum with chloride because bromine and chlorine are both halogens. Okay, so what do we know about chlorides? Well, they precipitate with silver, mercury, or lead. So magnesium has no solubility issues. And again, the same thing for bromine. We don't know anything about aluminum, but we know that bromine will only precipitate with silver, mercury, or lead, and this is just aluminum. So this is, again, aqueous. So this is the kind of way that you're going to have to predict precipitates in these types of reactions between pairs of ionic compounds. Having discussed how we predict solubility and such, we need to be able to write molecular, ionic, and net ionic equations when we combine pairs of aqueous solutions. So let's do one with silver nitrate and sodium carbonate and see if we can make our way through all the steps. To begin with, we're going to write the chemical formulas of the 2 substances and then predict the products by swapping the cations and anions, as shown at the bottom there. The A and C are swapping with B and D. And so now the silver is with carbonate and the sodium is with nitrate. Silver is +1, nitrate's -1, sodium is +1, carbonate's -2. And so that's how come you need to have a 2 in this formula and no extra coefficients needed on the sodium and nitrate. But the equation is not yet balanced. We need to put a 2 here in front of the sodium nitrate to get the number of sodiums to come out even. And also we would have to put a 2 in front of the silver nitrate to have the right number of nitrates, but that gives us the right number of silver also, which is good. That's a good place to begin. Now, after we write the chemical formulas of the products, using the rules for how you combine things with their charges correctly, what do we do next? Now we're going to write a molecular equation and predict the solubility and balance it. So I already did the balancing. We put the 2 in on the product and on the reactant side, and we predict the solubility. So how do we come up with those things? Thinking back to the solubility chart, the silver and carbonate, well, what do we know about either of them? They're not on the list. So if you don't see them anywhere, they must be a solid. The sodium and nitrate, it contains a sodium group 1A cation, but nitrate is also on the always soluble list, so that's how we know that that should be aqueous. This is the molecular equation. We write all of the formulas as though they are molecules. What's the next step? Now we write the ionic equation where we dissociate or list separately the soluble ionic compounds. So everything that's listed as AQ is soluble. And so the silver nitrate and the reactants are separated into 2 silver ions and 2 nitrate ions because of the 2 in front. Whoops, sorry about that extra line, folks. And 2 of those, so you have 2 of each ion. Otherwise, our equation is not going to be balanced when we get done. The sodium carbonate is also aqueous, so we separate that to make 2 sodium ions. Don't forget the 2 here counts. There's 2 ions of sodium separately. They're not stuck to one another at all. And a carbonate ion. The products then give us the solid silver carbonate, but you only separate the soluble compounds. So we leave that one as is. And then the sodium nitrate, which is certainly aqueous, there's 2 of them, so there's 2 sodium ions and 2 nitrate ions. The ionic equation is long and detailed. When you have to write one, there's a lot of parts to remember. Then to write the net ionic equation, we have to identify and eliminate the spectator ions from the ionic equation. The spectator ions, remember, are the ones which have no chemical change. And so which ones in this reaction have not changed from start to finish? So we'll look on the left side of the reaction and the right side of the reaction, and you see that nitrate is there twice in the exact same form, 2 nitrates, aqueous, so that's 1 spectator ion. And then the sodium is the other one. The sodium occurs as a reactant and as a product, and so it's the other spectator ion. So omitting them, eliminate them from the equation, then we have what remains down here, the net ionic equation. The net reaction then for silver nitrate with sodium carbonate is to see that the silver has combined with the carbonate to make this solid silver carbonate. And you always need some more chemistry humor. So if you're not part of the solution, you're part of the precipitate. Ha, ha, ha. So those things which are not in the solution, the ones that are in solution are the ones that we list as aqueous. And the ones that are part of the precipitate are the ones that we list as solid. Sometimes we misunderstand the notations, but we think about them, they might feel all right. Let's do another example or two and see if we can make sense of these picture diagrams, because I know they're not your favorite thing, but maybe they're okay. So we have some choices for anions on the left. There are nitrate, chloride, carbonate, phosphate, and cations that are just pictured as red here: calcium, silver, potassium, and cadmium. And we end up with this observed result. So we're pretending that these are aqueous ions and combining, and this looks like they're all together in an orderly fashion in the right, and that means that must be a solid. So which pairs of anions and cations could give you this kind of arrangement? Well, the first thing to notice is that the ratio of blue to red, or the anions to the cations, I guess that's a better way of saying it, the anions to the cations is 1 to 1. So anion to cation ratio is very simple and straightforward. So you have to have an equal number of each in the compound to make that work. And then it has to also be a precipitate when you combine them. All right, so let's see what our choices might be here. So if you were to consider the possible anions and things that they might precipitate with, well, you're never going to include nitrate because it doesn't precipitate with anything. Chloride could precipitate with something, so what could you put chloride with? It has to be silver, mercury, or lead. So it could be the silver ion, and so it could be chloride ion plus silver ion to make silver chloride solid. That's a possibility. But it would not apply to calcium, potassium, or cadmium. It's the only one with chloride. What about the other choices? How about carbonate? Carbonate, is that soluble with anything? Well, it's soluble if it's with a group 1 ion, but we're going to have to combine it with something that has a 1-to-1 ratio if this diagram is going to make any sense. So the carbonate with a -2 charge could combine with the calcium +2, and that would precipitate, because most things precipitate with carbonate. So calcium, carbonate, that's actually what's in limestone or chalk, honestly. And another choice with carbonate would be the other +2 cation that would work would be the cadmium. So cadmium, who cares? It's an unusual element from your standpoint. We don't run into it with as many examples. It's down there where we're looking for it. It's underneath zinc in the transition elements. It's a 2+ cation. Would make the same 1-to-1 ratio of cadmium carbonate, and that would also be a solid. Okay, so we got the carbonate figured out. What about phosphate? Could phosphate work in any of these examples? Would it precipitate? Yes, it would precipitate. Phosphate usually does precipitate, but only if you could find a 1-to-1 anion-cation pair would that be appropriate in this example. And this phosphate with a -3 charge would have to pair up with something that has a +3 charge, and there aren't any in this list of choices. So those would be the only 3 from this set of choices that would give you precipitates that show like that. Okay, here's another one. Let's see if this makes any sense to you. We have here a way of thinking about the mixtures of aqueous solutions of potassium hydroxide and magnesium chloride, and we want to make sure we understand what's going on in the solution. So picture the bluish portion at the top of the box as the aqueous part, and the gray at the bottom being a solid or a precipitate. So if you combined potassium hydroxide with magnesium, oops, I forgot to write aqueous. Put that in there and be complete. Sorry. Aqueous solutions of both. So aqueous potassium hydroxide with aqueous magnesium chloride, and we don't have to balance it to get this one right, but we could. What would the products be? So you get potassium with chloride, and we have to decide whether it's soluble, and then the other product would be magnesium with hydroxide. Oh, and magnesium with hydroxide is a +2 cation and a -2 anion, And now we have to remember our patterns for solubilities. Okay, so which things are always soluble? Well, potassium is always soluble, so we don't have to think any harder than that. But then we have to think about the magnesium and the hydroxide. Magnesium doesn't have any rules, but hydroxides do. And hydroxides are commonly not soluble, except for group 1 elements or barium, strontium, and calcium, the bottom of the group 2 elements. But magnesium is in fact one that's not soluble. So that one turns out to be a precipitate. Now, which picture? Oh my goodness, that's really messy. Let me adjust the view for a moment. Okay, better. Now, which picture represents this accurately? Well, obviously diagram number 1 lists potassium chloride as a solid. That doesn't make sense. And so does the last one. The diagram number 3 suggests all the ions are aqueous. Well, that turns out not to be true because magnesium hydroxide would be a precipitate. So diagram number 2 represents the magnesium hydroxide collecting at the bottom of the beaker or the mixture, wherever it is in, as a solid. This will conclude my discussion of the precipitation reactions and solubility guidelines. I hope you find this helpful. Good luck on your homework. Please ask more questions as needed, and see you in class.